Sorry about the crazy numbering, but this is solving quadratics using square roots. So if you look over here on the board, it's solving with square roots is the topic that we're covering first. Again, review from Math 2 and goes along with yesterday's video about breaking down square roots. We have two different topics we're going to be covering today. So solving with square roots is the first one. And then next we're going to do key features of polynomials. All right, you guys don't have to write down every problem right now. Just number 1 will be sufficient. So, or in this case, 14. Again, sorry about the numbering. So if we have this problem, 5x squared minus 180 equals 0, we want to solve it for x. What would you do to solve for x? You add the 180. Solve like normal. Don't worry about factoring right now. We're just solving like normal. Add that 180 over to the other side. So 5x squared equals 180. And then still solving for x. So what would you do next? Divide by 5. So grab those calculators. What's 180 divided by 5? 36. Now, once x squared is alone, because that's kind of like our goal is to get x by itself, here we have x squared. Now we get rid of the squared. How do we get rid of the squared? Square root. So x equals, what is the square root of 36? 6. But there's something that can go right in front of that. We talked about it back in Unit 3, but it's been several weeks. Does anybody remember anytime you take a square root? Plus and minus, that's right. The positive and the negative. Because if we were to plug this answer back in for x squared, any number that you square always becomes positive. So negative 6 squared is 36, and positive 6 squared is also 36. So either one of those will work. Okay. All right, write down our next problem. 3x squared equals 24. What would I do first? Divide the 3. I want to get the x by itself. I'm going to divide by 3. 24 divided by 3 is 8. Then I would square root. Now, from now on, are we putting things as decimals and estimating what that is? No, 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 no. We are going to make a factor tree, make some factors that we have. So with our 8, we're going to make a factor tree. Now, the hint from yesterday was to find the biggest perfect square that goes into that number. You can also just think about what multiplies to be 8. What are some things that multiply to be 8? 4 and 2. And 4 is a perfect square. So really what we're doing here is we're taking factors of the square root of 8, which are the same as saying square root of 4 times square root of 2 makes square root 8. But what we're going to do is we're going to break those down. So start off by saying x equals, and go ahead and put plus or minus. Now what is the square root of 4? 2. Can I take the square root of 2? No. I just leave it. And that is my answer. So just a little shortcut of what we did in Math 2. If you find that biggest perfect square that goes into that number, it makes simplifying it a little bit easier. So we end up with 2 square root 2. Okay, write down your next problem. 4x squared equals 25. Now, at this point, you should probably be able to recognize perfect squares, right? Especially after factoring all those difference of squares that we had in the last unit. So 4 and 25 are both perfect squares. But first thing we want to do is get x squared by itself, so we're going to divide the 4. Since they are perfect squares, leave it as a fraction. Leave those perfect squares in there. So 25 over 4 would equal x squared. Now, how do we get rid of the squared? Square root it. Now, when you square root a fraction, you can square root the top and the bottom. So x would equal, don't forget plus or minus, 5 over 2. Bless you. Because the square root of 25 is 5 and the square root of 4 is 2. So we just say 5 over 2. All right, then write down our next problem. X squared plus 25 equals 0. What would you do to solve for x? Subtract 25. So x squared equals negative 25. And then we would square root. So x equals plus or minus. Anytime you take a square root, go ahead and put x equals plus or minus. And then we have to square root that number. If it didn't have the negative with it, what's the square root of 25? 5. What do we do if it's got a negative with it? And good job. Y'all saw that on the video yesterday, huh? The square root of a negative, you put an I with your answer. That's right. And the I usually goes after the whole number that you have. Now, if you still had a square root in your answer, it would be before, in front of the square root, but after the whole number. All right, our last one we're going to do is this one. 3x squared plus 2 equals negative 64. Now think about getting x by itself. Imagine it doesn't say x squared. What if it just said x? We're just solving for x. What would you do to get x by itself? Good. So 3x squared would equal negative 66. Then you would divide by 3. So x squared would equal negative 22. Now get rid of the squared by square root. So x equals plus or minus. And then we look at that number 22. Okay, because 22 is not a perfect square, so if it's not a perfect square, you go ahead and make that factor tree to the side or think about, hey, what multiplies to be 22? Our only choices are either one of those perfect squares. Can we break it down even more? No. So the square root of 22 stays as the square root of 22, but it's negative, so we have to put good. I's go before the square roots, but after the numbers. So x equals plus or minus I square root 22. So even if you didn't watch the video yesterday, do you still kind of remember this from Math 2? Some of it might look familiar. Some of you might be going, no, I don't remember nothing from Math 2. If it was more than last week, it's out of sight, out of mind. But you got 8 homework problems that look like this. So get x by itself, square root. Don't forget plus or minus. Break down any square roots that you have. All right, so we've got 3 more examples we're going to do, and those 3 examples are on key features of polynomials. So if you want to, you might want to make a line across your paper and write key features of polynomials because this is a new thing, and I got to open up a new document for it because I accidentally split these up. So it might take a minute for that to pop up. I'm hoping today that I will finish your projects that you have, so you guys will get those back tomorrow. I just have this short little stack here to do, and a couple that are online that people submitted electronically. And then I have your test to grade that you took yesterday. And then so you might see some big changes in your grades on Infinite Campus because both of those counts as test grades. And as you know, test grades are weighted a little bit more. So hopefully yesterday's test was good, though. We will see. Yeah. Yeah, they they sent us an email the night before and said instead of working from 8 to 11, they said we were going to work from 8:30 to 11:30. And I said, "You can't change it the night before." But then they also got us Chick-fil-A. So then I was like, "Well, okay then. I accept these changes." Sorry, I thought this would pop up by now. Does everybody have their graph and calculator out? Because you're going to need it out for this next part that we do. So make sure you grab that graph and calculator out. Let's see if this has changed now. Come on. Ah, there we go. Okay, I'm going to shrink these graphs just a little bit, but then I'm going to make the overall page a little bit bigger. These graphs that I have here are just quick sketches that you would need to do. We're not finding the key features of these 4 little graphs. Oops. All right. Dun, dun. Okay, write down that sentence. Quickly sketch these graphs. Again, they do not have to look beautiful. I just found the first ones off of Google. Yes, you can. There you go. You're welcome. Bless you. Scared of graphs? Oh no, don't be scared of graphs. These will be a little bit easier. So these graphs that we're going to talk about today are all polynomial graphs. So these are different examples down here. Again, I just typed in Google and chose one of the first ones that popped up. So this one makes a line, so it is linear graph. Yep. And linear graphs start out as x, right? This one is a quadratic. I'm just going to put quad. I'm going to shorthand some of these so it has an x squared in it. Guess what this one is? Cubic. This is what cubic graphs look like. They have kind of some more curves in them. Here is an example of a quartic graph, but a quartic graph can also look like a quadratic graph depending on what the terms are in the middle. But a lot of quartic graphs make this a W shape, but they could make just a parabola shape. It really just depends on, again, what your terms are. And guess what this one is? Yep, this is a good example of a quintic or an x to the fifth. A quintic graph can also look like a cubic graph, just depending on what the terms are, again, in the middle. The key thing is the end behavior, which is like these two sentences, what they're saying up here. If the ends of the graph go in opposite directions, you have what we call an odd degree. Now, when you think about odd, you think about what numbers? That's right. So these are what we consider our odd degrees: linear, cubic, and quintic, because they have powers that are odd numbers, 1, 3, and 5. And those odd degrees go in opposite directions, and they have an odd number of x-intercepts. Here we can see 1 x-intercept. Here we see 3, and over here we see 5 times that it crosses the x-axis. Now, if it is the opposite of that, where it has an even degree, such as a quadratic and a quartic, then it has a even number of x-intercepts, and the ends of the graph go in the same direction. So this will be important when we find our x-intercepts, but also when we look at our end behavior of our key features. So key things to remember: odd degree, opposite directions, odd number of x-intercepts. So all the O's go together: odd, odd, opposite. And if it goes in the same direction, it has an even degree, and so it has an even number of x-intercepts. So let's do some examples. The first one we're going to start off with is a graph, and I do want you to sketch this graph as closely as you can, because we're going to see some as graphs and some as equations. So try to include the correct numbers. You don't have to do all the numbers, but try to make sure it goes to about the same spots as that graph does. Now I'm going to go through these in order, but you can also do whichever ones you feel comfortable with first. With polynomials, they are a continuous graph, which means they're going to keep on going. They're kind of like a roller coaster, right? It goes up, it goes down, it goes up, it goes down, but it's going to keep going in all of the directions that you have. When you do your homework, I have these drawn out for you. It's a worksheet, and I have all your 9 things listed. And when you take tests and quizzes, I will list these 9 things out so you can just write in what they are. Okay? So, first on our list is x-intercept. What does it mean to be an x-intercept? Where it touches the x-axis. So, here's my x-axis, so it hits at good. So my x-intercepts are at x equals -5, -3, 1, and 4. Now, how many x-intercepts do we have? There's 4. But think about those sentences you just wrote down. Those are 4, which means there's an even number because 4 is even. So the ends of the graph should go in the same direction. Do the ends of this graph go in the same direction? No, they don't. They go in opposite directions. So one of these has a multiplicity. So you get a multiplicity if it just touches the x-axis and bounces right back off. Do you see anywhere where it bounces? At 4. So 4 has a multiplicity of 2. We also call that a double root. Remember how we talked about that last Monday? This past Monday? So this one has a double root or multiplicity of 2. Because what happens is you think about direction. It's decreasing at that point at 4, but then it also increases again because it bounces off. So it's kind of like it hits twice. It hits it and then goes back up. All right, y-intercept. So here's my y-axis. If I trace along, then it hits my y-axis here, which is at -3.5. Yes, with graphs, you just estimate. So y equals -3.5. Next on our list, it says relative minimum. You already told me that the ends of this graph go in opposite directions. So do we have a true minimum? No, because this side's going down forever. But we have what we call relative minimums. These are any valleys that we have. So if I'm tracing along or looking at this, I have a valley right here, don't I? This is kind of like I about said valley again, but that really makes no sense. But it's kind of like a minimum where we have kind of swings down. Where's that minimum at? Y equals -6. Good. Remember, you use the y value when we talk about minimum because we're looking down here. Do we have another minimum? Well, right here we have another valley. Now, I know the x value is 4, but what's the y value? 0. So we have 2 minimum values. Look for those valleys. For max, you're looking for your mountaintops. Do I have any mountaintops here? Yeah, I got 2 again. I got one right here. Remember, we're looking for the y value. So the y value is 5. And I have another mountain here with a y value of 2. So y equals 5 and 2. Those are our peaks that we have. So we have peaks and valleys for our max and our min. And remember, min and max are talking about the y value, because if I say minimum, you all are probably going to go like this, right? You're going to put your hand down at the bottom. Would you say minimum and put your hand over here to the left? No, minimum is down here. Max is up here, so it's your y values. All right, end behavior. You want to look at the left side and the right side, and you want to look at where the ends point. So this end points down, so down to -infinity. And the right side points up to positive infinity. Up infinity. I like it. All right, intervals of increase, decrease, those are hard to think about, but I'm going to give you a trick way to help you out with it, okay? What I want you to do is at the bottom of your graph is to make a long number line that covers the length of your graph. Now, this number line is going to help us draw out sections where the graph increases and decreases. So first off, if I read my graph left to right, my graph is first increasing. It increases to this point right here. So my graph is increasing to this point. And then the graph goes decreasing to this point. So it's decreasing between here. Then it increases again to about here. And then it decreases a short little bit, and then good. Because graphs are continuous, that's what they're going to do with these polynomials. It's kind of like a roller coaster, right? So we're going to increase, decrease, decrease, and increase on up. Now what we have to do is find out these values that are going on this number line. If it's a number line, it's always x values. If I keep going left, the furthest number I'm going to get to is negative infinity. So negative infinity is going to go on the end. This number, our second number where we have our little dash, is the x value of here, because up here is where it stopped increasing. But we want that x value, which is about at -4, right? You could say maybe it's a little bit more than that, but we're just estimating. Then my graph, and if you like highlighters, this might be good to highlight. My graph decreases in this range to here. But what's that x value where it decreases to? -1. Okay, that will work. Then my graph is increasing to this point, what's that x value? Good. And then it decreases to, and then it increases again forever, so to infinity. So the ends of your number line will be negative infinity and positive infinity. Does that make sense? Good. So remember, these numbers, though, have to be x values. A lot of people like to change them to y values, but they have to be x's. Okay. Now we have to just say all of those intervals. Now, to say those intervals, pick them out like segments. It's increasing between these two, so between negative infinity and -4. So you write that as like a coordinate, negative infinity, -4. That is called interval notation. So when it asks for intervals, we can write them in this way. Okay. It also increases between -1 and 2. And then it also increases between 4 and infinity. So we're looking for all of those plus signs where it increases. So there are 3 spots on this graph where it increases. Now, where does it decrease? Good, -4, -1, because that's where I have the minus. And also between 2 and 4. So if you can make that number line and you can read the graph left to right, you're halfway there. You just need those x values and you put them in the parentheses. Okay, let's talk about domain. Now, domain is how far the graph goes left and right. So do we have any points where it's not going to keep going in either direction? So it's all real numbers, that funny looking R. Now, range is how far the graph goes up and down. Infinity. Instead of infinity, though, we put all real numbers. And you can really get that idea from the end behavior. One side goes down, one side goes up. So if one goes down, one goes up, we're covering everything that we need up and down. All right, we have another graph that we're going to do, and I realized just in first period that part of my graph was cut off, so I'm going to add to it a little bit. But we're still finding these same 9 things for this graph that we have. And I'm going to add some to my graph up here. I have no idea why it decided to chop itself off. Well, and I'm just going to have to extend it a little bit to make it look a little bit better. I didn't really have enough room, but you guys can make it look better than how it looks on my paper. Oh. Now again, when I give you a graph, you just want to estimate where these points are. You don't actually have to go through and try to figure them out to be exact. So when you're given a graph, you're just estimating the points. What are the points going to be? About where are they? So your answer should be something like a whole number or 0.5. I wouldn't get any more technical than that with trying to find out where these are. There are ways to find them exact, and we will probably do that when we review for our EOC, because you can type it in Desmos and get a better picture than you can on your calculator. All right, so let's start off with our x-intercept. So our x-axis is here, so it hits at 1, 2, and 3. Yep. Now, how many x-intercepts is that? 3. Should it have an odd number of x-intercepts? No, because the ends of the graph are going in the same direction. So one of those has a multiplicity. Which one? 1. So I would say x equals 1 has a multiplicity of 2, and then you could say x equals 2 and x equals 3. So now we have an even number. X equals 1 occurs twice, then we have 2 and 3. Exactly. Anytime it just bounces off the x-axis, put multiplicity of 2. If it crosses, then it's just the 1. All right, y-intercept, sorry about my graph, but where does it hit the y-axis at? At 4, so y equals 4. Okay, relative min. Min's the valleys. Do you see any valleys? There's 2 of them. One here, one here. So remember, minimum are the y values. What are those y values? So what's my y value right here? 0. What's my y value right here? Good. Y equals 0 and negative 1.5. Okay. Max or any mountaintops? Got one right here. That's about at 0.5. So y equals 0.5 would be my mountaintop that I have. All right, let's go with end behavior. So what happens to the left side and the right side of my graph? We already said they both go in the same directions. They both go up to and beyond. Good job, Buzz Lightyears. Yeah. No, you got to use y value, not x value. Yeah. So on the max min, use the y value. Okay, intervals of increase, decrease. Let's make that number line right underneath our graph. Okay. You can go ahead and put negative infinity and positive infinity on that number line because that's where you have some transitions. And then look at your graph. First, the graph is going down. It is decreasing to this point right here. What's this x value? Because now we do x values. 1. And then my graph goes up. So it increases to this x value. What's this x value? 1.5. And then my graph is decreasing to here. Now again, x value is, oh, nope. That's the y. We need the x. There you go. And then last, my graph is increasing. So it will always alternate. So if it starts off decreasing, then it's going to increase, decrease, increase, decrease. And remember, you need the x values. Now, what you might also want to do, if this helps you, then do that. Write these as coordinate points. This is the point 1, 0. This is the point 1.5 and 0.5. This point would be 2.5 and negative 1.5. And then again, we're using the x values for intervals of increase. So those x values are what's going to be on that scale. Okay. So now let's write down the intervals that increase. There are 2 intervals that increase. They are at good. So between 1 and 1.5, 2.5 to infinity. Where do I decrease? Start at the far left. What have I got? Negative infinity to 1 and to 2.5. That's right. So look at those intervals where that graph increases and decreases. You always want to go left to right. You always want to write your intervals as the smallest number to the bigger number. All right, domain. How far does the graph go left and right? Always. Really, with all polynomials, everything in this unit, that domain is all real numbers because it's continuous. It's going to keep going. Range on this one, look at your end behavior. Both the ends go up. So is it all real numbers anymore? No. Your range is going to deal with your y values. Since both parts go up, we would put well, then we need our lowest point. So look at your minimum. Which one's lowest? Negative 1.5. Because this graph, there's nothing below this point right here. And you could think about it as like an extra little like dotted line in here. Everything is graphed above this line. There was nothing below. So use that lowest value that you have, negative 1.5. All right. So on graphs, again, just estimate where they are. Use the best to your knowledge to figure out what is what. If you are within a point, then I will count it right. So if you would have put this range as negative 5, I wouldn't count that. But if you put negative 2 instead of negative 1.5, I would count that number. But now let's look at what if we have the same type of question, but I give you a specific equation. There it is. Let's see if I can get that equation straight. This is the equation that we're going to find our key features of. Now, in the last two problems, we needed to see a what? A graph. So guess what we're going to have to do if we have an equation? Put it into the calculator. So that's how we want to start this one. You can go ahead and go to y equals once you've written down these things and type it in y equals and go ahead and look at our graph. Let's see what that graph looks like. I don't know if I already said this or not, but on your homework, these things are written down for you. On your tests and quizzes, your 9 things are written, so you don't have to remember what key features you have to find. Okay. I can't remember when I say things. Maybe I didn't even tell first period. That's probably what happened. Probably told y'all twice and forgot to tell first. Did I? We'll see. No. Short-term memory loss here. All right, so let's go to our calculator, go to y equals, type in that equation, and then hit graph. So it should look like that picture there. If yours looks different, don't forget, how do we get back to our standard window? How do we get back to our standard window? Zoom 6. So if your graph looks crazy, a little Zoom 6 will help you out. Okay, I'm going to tell you how to find x-intercepts on your calculator. There are 2 ways that you can find your x-intercepts. So way number 1 is just to look at your graph. Where does it look like it crosses at? If we start with this one here on the left, I would probably say -4. So if you hit trace and type -4 and enter, is that an x-intercept? How do you know? Y equals 0. As long as y equals 0, that's an x-intercept. I heard you guys also say -2, so you can just hit -2, enter. Is that a y-intercept? Yes, it is. What's the other one? 1. 1, enter, works. So there are your y-intercepts. X equals -4, -2, and 1. Do any of those have multiplicities? No, they don't bounce off, right? They all just cut through that x-axis. Do you think you're always going to have nice, pretty whole numbers? No. So let's refresh on how to find it if it's not a nice, pretty whole number or if you're unsure. So everybody hit second trace. What's another word for x-intercepts? 0. So choose option 2. Now your calculator won't just tell you what it is. It wants to know, hey, about where are you looking at? So let's say that we were trying to find this one that we think is at 1. So it says, hey, tell me a number to the left. What's a number to the left of 1? 0. So hit 0 and enter. Then it says, hey, tell me a number to the right. What's a number to the right of 1? 2. So we hit 2 and enter. Your calculator will say guess. You always hit enter when it says guess. And it says, oh, the 0 is at 1. So let's do that one more time to make sure you can see it. So it's second trace option 2. And then you say a number to the left, you say a number to the right. So if I wanted to find this one down here that I think is at -4, I'm going to say -5, enter, -3, enter, and enter on guess. Remember, if it gives you like a y value like this one does, it's that scientific notation since it has the e in it, so it's basically just 0. So our 0 is at -4. We just looked at the x value anyway. If you need help with that, let me know because you're going to have about 40 minutes to work on homework, so I will help you with your graphs and your windows and all that stuff. All right, next on the list is a y-intercept. What does it mean to be a y-intercept? It's where the graph touches the y-axis, also known when x equals 0. So if you want to hit trace and hit 0, enter, when x equals 0, my y-intercept is -8. For everything else that you have, I would just make a quick sketch of this graph on your paper. A quick sketch kind of looks like this. You don't have to put the x-y axis in, just sketch that shape that it makes. It makes like a U shape. So what we want to look for next is a relative minimum, which our relative minimum is right here, right? Now, we are not going to estimate if it gives us a formula. We are going to use the functions on our calculator. So, second trace, go down to option 3, which is minimum. Now, what you want to do for this one, you can type in numbers or you can move your cursor. About there's the minimum, so I'm just going to move mine somewhere to the left and hit enter. And then you move your cursor to the right, hit enter, and enter on guess. Now I'm going to give you a hint. The x value is going to deal with your intervals of increase, decrease. So write this down as a coordinate point. You're going to have to round to 2 decimal places because it's not a pretty whole number. So my minimum is at negative 0.21 and negative 8.21. So negative 0.21, negative 8.21. But what do I write down for relative minimum? Because I don't write it as a point. I write it as the y value. So my y value is negative 8.21. Let's do the same thing, but find that minimum. So we're finding the peak that we have up here, and we want to find it as a coordinate. So back in our calculator, second trace, option 4 for max. Move that cursor over. You want to move it to the left of the max. Doesn't matter how far, just somewhere to the left. Hit enter. And then move it to the right a little bit. And enter on guess. So my max is at about negative 3.12 and 4.06. Now again, for my max, what value do I use? The y. Don't write it as the point, just write down the y value of your max. So second trace will be your best friend with finding x-intercepts, your min, and your max. All right. End behavior. We can just look at the graph for this. What happens on the left side? Down. So right side. Good. Left side's going down, negative infinity. Right side's going up, positive infinity. Knowing that information, we can answer our range. What's our range going to be? All real numbers. One side goes down, one side goes up. All right. Let's talk about intervals of increase, decrease. To do that, we need a what? Number line. Here we have our negative infinity. Here we have our positive infinity. Now just read the graph left to right. The graph first, then, and then. So there's only a couple of changes here. We increase, we decrease, and we increase. So all we need to figure out is the x values where that occurs at, which is the x values of our max and min of our points that we have there. So here we're going to have a negative 3.12 and here a negative 0.21. So if you need to, make yourself a little note. These are the x values of your maxes and your mins. Dun, dun, dun. It's like magic. Just like magic. Or not. Okay, what are the intervals of increase? And we have another one from good. And what's our intervals of decrease? Very good. So it only decreases in that one spot in the middle. It increases on the two ends. And what do we say for domain? All real numbers. Very good. All right, your homework is the worksheet. On the front, you have 5 problems where you find your key features. Now, if you want to go from most challenging to least challenging, I would do the 3 problems that have the equations first because you might need some help with your graphs. So if you want to start with those first, and then you can do just the graph ones. And on the back, there are just 8 square root problems. Those go really fast on the back. Oops. They stuck together. All right, so there you go. Of course. Here, pass one of those to Corin on your way because I cannot. Here you go. Pass one to Paige. Yeah, sure. And there you go.